So topics tomorrow. I have this on my website as well under tomorrow's day. No calculators. I think we've gone through inverse trig derivatives. We've done implicits. Today, I'm going to focus on particle motion and curve sketching. Okay, those are the two big ones I want to focus on today. Make sure that we know our unit circle values. Make sure that we know our big derivative rules, e to the u and natural log of u. So I want to start off by having us practice through our derivative rules again. So if you guys get out a sheet of paper, let's practice our 6 original derivative trig rules, and then we'll practice through our arc trig rules. And then I also want you guys to make sure that you can still recall e to the u and natural log of u. Those are the big ones. Okay, go ahead and jot those down for practice purposes.
That's a good issue.
Okay, are we ready to check? Yes, question?
Are there going to be like natural laws?
Yeah, just want you guys to know these rules. Yeah, so you may have a derivative. Won't be any curve sketching, but I'm actually for the derivative of natural log of u.
Can you write it? Can I?
Yeah, I will. I just want you guys to try this first, and I'll write it stuff.
Oh, okay.
Because I want you to see if you can remember those major rules first, and then I'll go over them. Okay, are we ready to check the 6 original trig rules here? Okay, are we good with these? So let's practice our 6 arc trig rules, arc trig derivatives. Remember, there's only 3 that you have to worry about, right? The first column and the second column are just negative versions of the one next to them. Mm-hmm.
On the side, you have this power rule, but since when do you multiply by new time?
That's just basically a reminder of chain rule. So if I have like y is equal to x squared plus 3 to the 4th, that's really its power rule and then the chain rule. Yeah, it's really just a chain rule. That u prime is included for all of our derivative rules. Just a reminder of chain rule to look for it. Okay, have we had a chance to write these rules down? Okay, let's check these rules. Okay, let's go through rule 2 and 3 here. What's each of the u's rule? Yeah, the original function times the exponent's derivative. Okay. And then natural log of u is, so make sure we know these are the big three that will show up again and again.
Shooting. Can you draw the graph again of the natural log of u? So for e to the u at 0 is equal to 1. At x equals 0.
Yeah, it's 1. And it's always going to hover above the x-axis. It will never touch the x-axis.
For ln x, when does ln x equal 1 have to?
Natural log of e.
Oh, okay.
Let's see what's the
Thank you.
All right, let's go to worksheet 3. I'll give you guys a chance to look at this some more. But next up, we're going to go to worksheet 3. We'll do a full curve sketch problem, number 6. Worksheet 3, last problem in your worksheet packet. Okay, so we know the drill. We're just going to go through, find the derivative, slope sine line, test subintervals, second derivative. Yeah, number 6. All right, anybody still need this to look at this? All right. Number 6. Okay, so sketch the graph of the function 1/2 x minus cosine x on the interval from negative pi to pi. Find order pairs of absolute and relative extrema, intervals increase, decrease, intervals concave up, concave down, and point of inflection. So let's start off with f prime. Power rule, first term, 1/2 x becomes 1/2. cosine x becomes, yeah, so the two negatives will cancel each other out.
We just did that, do 1/2 plus sine.
Sure. Mm-hmm. Okay, so there's our cleaned up f prime function, set equal to 0 to find our critical points. Get sine x by itself. Okay, so now we have to ask ourselves, where is sine equal to negative 1/2? Yeah, third and fourth quadrant, variations of 5/6. Okay. 7 pi/6, and good. Okay, so we have to be careful though, because these are what lands between 0 and 2 pi, but we only want the values between negative pi and pi. So if we look, if you just don't even think about pi, just think in terms of the coefficient, right? Between -1 and 1, 7/6 is to the right of 1, so that's outside the interval. 11/6 is almost 2, that's also to the right of 1. So these are outside the interval. But we can always find coterminal angles by adding or subtracting 2 pi. And here, because we're extending to the negative region, let's test out subtracting 2 pi to see if our coterminal angle could land inside the interval. So if I want to subtract 2 pi from 7 pi/6, I want to match common denominators. I'm just going to subtract 12 pi/6 just to see if I have any critical points that will be that will fit inside our interval. So 7/6 minus 12/6 gives us what? -5/6. And then 11/6 minus 12/6 is negative, right? -5/6. And if you think about these values, right, -1/6 is to the right of -1, so we can keep that. -5/6 is also to the right of -1, so we can also keep that. So we have two adjusted critical points that do end up on our slope sine line. Okay, if you're having trouble locating those values, just pretend like you don't see the pi's and just think in terms of the fractional bit. You're just putting these fractions on the number line. Okay, everybody good with those numbers and those values? Okay, so next up, we have to find critical points in each subinterval to test against the f prime function, because we want to know whether each interval is rising or falling. Now, between negative pi and -5/6, it's tough to find a special angle, so let's just skip that one. Okay. Now, I will say that if there's one that you can't find, just know that they will all oscillate. Okay, so if you have a sign for one, you know the other ones are just the ones I give you will keep increasing, decreasing, and alternate slope between each subinterval. So let's do this one, since we can find something between -pi/6 and -5/6. I can choose -pi/2. And then between pi/6 and pi, I'm always going to take advantage of 0 if I can use it. Okay. If it's a slope sine line, we're always testing against the derivative function, right? The slope function. So f prime of -pi/2 . If you don't recognize -pi/2, you can always add 2 pi to make it fall inside the interval from 0 to 2 pi. So -pi/2, if I add 4 pi/2, that's the same thing as sine of 3 pi/2. So same thing as sine of 3 pi/2. What do you know about sine of 3 pi/2? It's negative what? -1. -1 plus 1/2 is negative. So I know that my middle interval is going to be decreasing. Okay, let's test 0, f prime of 0. Okay, thank you. Sine of 0 is going to be 0. 0 plus 1/2 is 1/2. And I know I can't find anything here, but my graph is just going to oscillate, so I know it's going to be increasing here. Okay, questions here? So we're going to go back and find those order pairs, but right now, what do you expect at -5/6? Relative what? Relative max? What do you expect at -5/6? Relative min. Okay, so you know how the graph is going to move. We'll come back and gather more information when we're ready to sketch the graph, but we're going to move on and finish off the calculus portion, move on to second derivative. Yes?
So, now you said it's like for sine and cosine, once you find one section, just do the opposite for your
But I want you to test them if it's possible. But if it's outside, if it's difficult to test without a calculator, you can just use the fact that it's oscillating.
This only applies to sine and cosine?
Yes, but I'll give you a sine or cosine on the test tomorrow. Yeah. Okay. Moving on to f double prime. Okay, so second derivative, 1/2 goes away to 0. Sine becomes what? Cosine. Okay, so there's our second derivative. We're going to set that equal to 0. All right, so where's cosine equal to 0? And 3/2. Okay, so we just want to just list out what we know, and then we can decide whether we need to make any adjustment. Now, pi/2 is safely between -pi and pi, but 3/2 is going to be to the right, or it's going to be outside my interval. So, but we also may need to test some negative values. Let's subtract 2pi to see if we have any that that we can use. So if I subtract 2pi, the same thing as subtracting 4pi/2, just to match common denominators. Okay, so what's pi/2 minus 4pi/2? Negative 3pi/2. 3pi/2 minus 4pi/2. Negative pi/2. Okay, so let's see which one of these we can fit. So it looks like pi/2 and negative pi/2, 1/2 and negative 1/2 will fit nicely between -1 and 1, but 1.5 and negative 1.5 is going to be too much outside of our interval. Okay, any questions about locating additional critical points and determining whether they fall inside our interval or not? Okay, let's find some test points. This right. No, you will not have to subtract. You can just, yeah, you can just keep pi/2 and that's it, right? Okay, so between -1/2 and -1, I can think of -0.75, which is -3pi/4. Between -pi/2 and pi/2, I'm going to take advantage of 0. Between 1/2 and 1, I can think of 0.75, which is 3/4. We're going to test all this against the second derivative function. Okay, if you don't recognize -3pi/4, you can always add 2pi to make it into a coterminal angle that you can recognize. So this is Cosine of negative 3 pi over 4 is the same thing as cosine of 5 pi over 4, right? Negative 3 plus 8 is positive 5. So cosine of 5 pi over 4, this is in the third quadrant. What do you know about cosine in the third quadrant? Negative, right? Cosine is positive in the first and fourth quadrant. So if you want to utilize, understand, ASTC here, right? All trig functions are positive. Only sine is positive. Only tangent is positive. Only cosine is positive. So second and third quadrant will be negative for cosine. So we know second derivative is related to concavity, so concave down. Next up, we test 0. Cosine of 0 we know is 1, so that's positive. Concave up. Next up, f double prime of 3 pi over 4. Cosine in the second quadrant is also negative, so concave down. Okay, we've done all the calculus necessary. Now we're going to go back, gather information about ordered pairs, and start sketching the graph. Okay, any questions up to this point? All right, does anybody still need this? So the most important ordered pairs are going to be your endpoints and your relative max, relative min. The point of inflection ordered pairs are not as important because you can kind of just estimate where they fall along the path of the graph. But we definitely need to have an idea where these points are. So let's practice gathering these ordered pairs here. Endpoints and relative max, relative mins. So let's start off. Now, if I want to find endpoints and these locations of relative max, relative min, they all go into the original function, right? We're done with the calculus. Now we're just trying to find locations. So let's start off with f of negative pi. Now, I want us to be able to just make some general ballpark values, right? I'm not so concerned about that you're getting all these decimal values correct. I just want you to be able to do some basic estimations. So whenever you see pi or negative pi, just treat it like 3, right? It's close enough to 3 where we can make a pretty good estimation for that value. So I'm just going to plug negative pi in for all the x's. Negative pi over 2, think of this as 3, so negative 1.5. Negative 3 over 2, so around negative 1.5. Cosine of negative pi, if you don't recognize cosine of negative pi, you can add 2 pi to this, which will turn into pi. Cosine of pi is negative 1. Negative times negative is positive, so plus 1. This is going to be around 0.5. I'm sorry, negative 0.5. Okay, let's find the other endpoint, f of pi. Treat pi like 3. Cosine of pi is negative 1. 2 negatives becomes positive. 1.5 plus 1 is around 2.5. Okay. Relative max, relative min, we also need to find those points as well. So this gives us negative 5 pi over 12. So think of this as negative 15 over 12. You know, negative 15 over 12 is slightly more than 1, but definitely less than 2. So just choose any decimal you want, maybe negative 1.2 or 1.3, right? You just know kind of generally where it's going to be. That's all you need. Cosine of negative 5 pi over 6. If you don't recognize that measure, you can add 12 pi over 6. It's really the same thing as cosine of 7 pi over 6. You know, cosine of 7 pi over 6 is in the third quadrant. It's negative, and it's going to be root 3 over 2. Two negatives will become positive, so plus root 3 over 2. I'll give you a guide for radical values. So if root 3 shows up, I'll tell you it's around 1.7. If root 2 shows up, I'll tell you it's around 1.4, just so you can have some idea to kind of work with. So that's pretty close to 1.8, or divided by 2, I'm going to get around like 0.9-ish. Okay, so if you're off by decimal, I mean, our decimals don't have to match. We just want to have some idea where these points could be, right? So that's all I want us to do, is just have some general ballpark values. That's good enough. Okay, I'm not going to be grading based off of how accurate your estimations are. Okay, f of pi over 6, or negative pi over 6. Okay, 1/2 times negative pi over 6. Again, treat pi like a negative 3. So this is negative pi over 12, negative 3 over 12, which is around negative 1/4, so negative 0.25 or negative 0.2. It's good enough. Cosine of negative pi over 6, that's same thing as cosine of 5 pi over 3. We know this is a positive, root 3 over 2, with a negative in front, the minus root 3 over 2. So negative 0.2 minus 0.9, so it's around negative 1.1-ish. Okay, so just this should be enough for us to kind of have a general broad strokes of our graph. So here's our sketch. We start off at negative pi. It's going to be negative 0.5. Pi is going to be at 2.5. Negative 5 pi over 6. It's going to be at negative 0.3, so I'm just going to make it a little bit higher than my endpoint. And then negative pi over 6 is going to be down at negative 1.1-ish. So ultimately, once I find my ordered pair, it should match our slope sine line, right? So let your slope sine line be your guide, right? You don't want to, if your ordered pair doesn't quite match your slope sine line, then go back to your slope sine line and use that, because maybe your ordered pair was a little bit off. But we know we want to increase to a relative max at negative 5 pi over 6. So it's a slight increase here to a relative max. It's going to decrease to a relative min at negative pi over 6. And it's going to increase the rest of the way. Okay, I don't know curvature information yet. I just want to have an idea of the path. Okay, that's my first run through sketch of the graph. Now I'm going to go back, look at the second derivative, and see if I can give it more detailed curvature along the path. Okay, so right now my graph is just based off of my slope sine line. Questions? Yeah. Mm-hmm.
I mean.
Oh, this right here.
Yeah.
Okay, next up, let's go to our concavity sine line. Our concavity sine line shows that we have a point of inflection at negative pi over 2 and point of inflection at pi over 2. So we'll estimate where those values are. Negative pi over 2 is somewhere between negative pi over 6 and negative 5 pi over 6. So I'm just going to kind of mark off. And then pi over 2 is somewhere between 0 and pi. Okay. We know that our graph is going to exhibit concave down initially. Shifts over to concave up between negative pi over 2 and pi over 2. And then the rest of the way, it'll be concave down. Okay, don't add any new path to your graph. You're just changing, adjusting the curvature within the path that you have. Okay, if I ask you for absolute max, absolute min, you just base it off your graph. Absolute max is going to be around around 2.5, and your absolute min is going to be around negative 0.5. Or sorry, negative 1.1. All right, so I want you guys to practice filling out your interval increase, decrease, point of inflection, relative max, relative min, and also practice writing out your because statements. I'll be looking for that tomorrow on your test as well. So filling out that information should be easy, right? You're just looking at your sign line and just putting those into interval notation in words. Explain the graph? Yeah, so are you good with these ordered pairs here?
Yeah, I just like don't know how to like actually with.
Okay, so I have my endpoint with these. So here, this is around negative 0.5. This is around negative 0.3. This is around negative 1.1, and this is 2.5. So just following the path of the graph, I know that from negative pi to 5 power 6, I'm going to be increasing. So my graph is going to be rising to my relative max. And then from negative 5 power 6 to pi over 6, I know my graph is going to be decreasing to my relative min. And then from my relative min to my max, to my endpoint is at 2.5. So I use my dotted line just to kind of connect those points.
Oh.
And then the second part is where I plotted my points of inflection, which is around negative pi over 2 and pi over 2. And then I just adjusted my curvature, right? I know my first interval is going to show concave down, so I just want that to be concave down. And then the second interval is going to be concave up, so concave up. And a third interval, concave down. So I'm going through the graph twice. The first time is just using my sign line, my slope sign line. The second time, I'm just using the curvature and adjusting it along the way. Does that make sense? Okay. Okay, so see if you can fill out those, fill out these values. Number 6, right? Relative max. So everything here, you can just pull from your sign lines. Because statements for for A, B, and C. A, B, and C, I'm going to be asking for because statements for all of them. The ones that students struggle with the most is relative extrema. So make sure that relative extrema also has because statements. I know I didn't put it on the key, but I'll ask for it. So relative min would be because f prime changes from negative to positive. Relative max would be because f prime changes from positive to negative.
Are we gonna get a calculator to like find the decimal point?
No calculator.
We just estimate.
Yeah, just estimate. Yeah, just estimate.
Kind of saying you're in the general ballpark.
Yeah, if you're in the ballpark value, I'll give you some guides. Like if it's root 3 or root 2, I'll tell you it's 1.7, 1.4. But I'm not going to be grading if you're off by a decimal value. I just want you to try to estimate those values, right? I mean, the accuracy is not as important as the work that you're going to show me.
How On the AP exam, do you get calculator?
On the AP exam, it's going to be, the format is going to be a little bit different. You know, I would say less than a third of the test is calculator and the rest of it is non-calculator. So majority of your AP exam test is going to be without calculator. All right, so let's see, we can check how we did here. If you just use the decimal values for relative max, relative min, I'm okay with that. But just make sure that you are understanding how to write those because statements. Okay, the next big thing I want to go over is the particle motion problem. So you guys can get a sheet of paper. I'll leave this up for another minute, but I want you guys to do a problem that is not on the packet. It's a 9. Okay, are we good here? Anybody still need this page? Okay, here's number 2, particle motion problem. You guys can copy this down. Okay, particle motion problem. We have a position function given. We're going to find the derivative to get to the velocity. And then we're going to gather information at the velocity level. Okay. We need to know how to apply rule for e to the u. Okay, so e to the cosecant of t, we know the rule for e to the u is e to the u times u prime. So what's the velocity going to be? Times. Good. So u prime is the derivative of the exponent. Cosecant becomes negative cosecant cotangent. So that's part A. Part B, find where particles at rest. How do you do that? Set velocity. Okay, I'm going to set velocity equal to 0. I'm going to clean this up a little bit. I'm going to pull this negative in front just to make it so we don't lose track of it. But you don't have to. Just I find it a little cleaner with the positive and negative in front, coefficient in front. Okay, we'll set our velocity equal to 0. Cosecant P. Okay, each piece I'm going to set equal to 0. All right, so this first part here is e raised to any power. Is this ever going to be equal to 0? No, right? You know that your exponential function graph is always going to hover above the x-axis. I'm going to ignore the negative. Negative is just -1 here, but and it's never going to hit the x-axis, so we know we're never going to have any critical points for exponential function e. Okay, what's a easier way to think about cosecant? Yeah, anytime I can think in terms of sine and cosine, it's just we're just more familiar with it. So is there ever a t-value that we can think of where this fraction can ever be 0? No, right? I mean, if I find a value where that causes sine to be 0, that will be 1 over 0, which is not the same thing as 0. I'm never going to get a 0 over 1 or 0 over a non-zero. So this is never going to happen. Okay, so nothing here. So let's move on to cotangents. What's the easier way to think about cotangent? Yeah, so anytime we think in terms of cosine and sine, we'll have an easier time. Now I want to find out where cosine over sine is equal to 0, but do I look both locations? Just what? Just numerator, right? If I set the denominator equal to 0, that's going to tell me where the fraction is undefined. That's not what we want. We want to find out where the numerator is 0. The value is 0 is only when the numerator is 0. So we only care about where cosine is equal to 0. Okay, where's cosine equal to 0? Okay, we check back with our interval. Do both these values fit? Just pi over 2. So that's the only value that's going to go on our sine line. But for part B, it's only asking where the particle is at rest. Our reasoning is because v of t.
The particle is at rest, we don't have to plug it back into the position.
Nope, we don't. When v of t is equal to 0. Oh. Part C is asking, find the interval where the particle is moving left and right. So we're going to create our velocity sine line here. And test our subinterval. Okay, endpoints. Critical points. Okay, we'll test all this against our velocity function. Let's choose convenient values that we can find between pi over 6 and pi over 2. I can choose pi over 4. Between pi over 2 and pi over 6, I'll choose 3 pi over 4. Okay, insert into the velocity function to test them. So I'll test v of pi over 4. Okay, so the negative is going to stay there. E raised to any power is always going to be what? Positive. Cosecant of something in the first quadrant is positive. Cotangent of the first quadrant. So this is going to give us what? Yeah, so only one negative, everything else positive. So I know that my particle is moving to the left in this first subinterval. Okay, any questions there? Yeah.
What'd you say about like like?
Yeah, e raised to any power or e raised to anything is always going to be a positive value.
Yeah.
Sorry? Yeah, I'm treating the negative as a -1. So it's a -1 times a positive times a positive times positive. So there's only one negative, so that negative will cause all those terms to be negative. All right, let's find v of 3 pi over 4. So I have a negative here. E raised to any power is positive. Okay, cosecant. Maybe something that's easier is thinking in terms of sine, because cosecant and sine will have the same behavior in terms of positive and negative. So think of this as sine in the second quadrant. What's sine in the second quadrant? Positive. Cotangent, think in terms of tangent. What's tangent in the second quadrant? Negative times positive times positive times negative. I have two negatives, so positive. Okay, we can make statements now about when the particle is moving left. This interval because velocity is less than 0. Moving right. This interval because v of t is greater than 0. Yeah.
Like the negative and the positive from like the
Right, so that negative came from the fact that if we go back to the derivative, e to the u, e to the cosecant of t, became e to the cosecant t times cosecant's derivative, which is negative cosecant t cotangent t. So I just pull that negative in front so I don't lose track of it. Because they're all being multiplied, so I just move the negative in front. I can move a -1 wherever I want to. So it's -1 times e to the cosecant t times cosecant t times cotangent t. So yeah, if you want to put a -1 instead of a negative, you can. Just think of that negative as a separate coefficient in front of all those terms. Okay, let me just spend the last few remaining minutes just going over problems that I did in the help session. So if you look at number 2 here, this problem, you'll see a problem like this where you're asked to find a derivative involving arc trig. In this case, though, there's a need for product rule because you have two terms being multiplied, and there's a need for e to the u. So you apply product rule, and also remember to involve arc cosine's derivative, which is basically arc sine with a negative in front. And I'll have this under this morning's worksheets if you want to look at that. And in number 3, you'll see a problem like this too, where implicit is involved and product rule. Okay, so tomorrow, help session, 7:15. I recorded the previous help sessions on my website as well, so you can watch those or work through those problems. I would say just like the implicit differentiation problem.
Okay.
Yeah.
So for the help session, is it gonna be on Teams? So like.
Yeah, it'll be on Teams. I'll send you guys a link if you're at home.
You don't like it? I like it.